This talk is called Pooled Testing to Isolate Infected Individuals. My name is Matthew Aldridge. I'm a mathematician and statistician at the University of Leeds in the north of England. So this talk will be about using the normal group testing process, but our goal is going to be slightly different. Our goal here is to use a limited number of tests the best we can, rather than to work out how many tests we need to do something. That is, we're going to assume that the number of tests we have available to do our pooled testing is constrained, and so we're not going to be able to find everyone with the disease, but instead we're going to use our limited tests as well as we can. So let's start by setting out the problem. So this is the problem we're looking at with pooled testing. As a reminder, this is how pooled testing works. Here I have 40 people, of which 4 of them are coloured in red to denote the fact that they are infected. So we could test these 40 people individually using 40 tests, and that would find which ones have the disease. Alternatively, we could use pooled testing. This example here is Dorfman's algorithm, an idea due to Robert Dorfman in the 40s. And the 40 individuals have been split into 8 groups of 5. And so each of these is pooled together. So in this top one, we take a sample from each of those 5 people, mix the sample together and test it. And because one of those individuals is infected, that means we get back a positive result from this top left pool. This top right pool, no one in that pool is infected, and so that test will come back negative. This pool down here, the 4th pool, this has 2 infected people in it, but we still just get a positive result. We don't get any special information about there being 2. So from these 8 pools we get positive, negative, negative, positive, negative, negative, positive, negative. We can rule out the negative tests because we know all of those people are non-infected. And then Dorfman's suggestion for his algorithm, Dorfman's algorithm, is that anyone who was in a positive test, we give them an individual test in the next stage. So that would be 15 more tests there. So we did 8 pooled tests in the first stage and then 15 more individual tests for 23 tests overall, which is less than individual testing, which is why that pooled testing can be better than individual testing. So the setup is we have n individuals. The prevalence of the infection is p, which we're modelling here as each individual is infected independently with probability p. And we have available t-tests of the form, does this pool of individuals contain at least one infected individual? Because that's how a PCR test on a pool of people would work, for example. At this point, I feel I should drop in an advert for this survey paper I wrote with some colleagues recently. This is a good survey of the kind of state of the art of pooled testing as of a couple of years ago, and I always want to make sure to drop in an advert for that into my talk. So the traditional pooled testing problem is this: given a number of individuals n, and given a prevalence p, how many tests, I'll call it t star, do we need to reliably find out all the infected individuals? But in this talk, we're interested in a different problem, which is a problem that people have been facing during the COVID pandemic. And that's this: given the number of individuals n, given the prevalence p, but given a fixed number of tests available t, how do we make best use of the limited tests? Because we've all heard stories in the news of where there have been shortages of tests, and so this is trying to model that. We perhaps don't have as many as the t-star test that we'd like in order to find everyone. So if we have t-tests, which is fewer than t-star, how should we try and make the best use of those tests? So the solution that this talk proposes is this, which is that we should make the best use of them by finding infected individuals with them. Because if you can find an infected individual, you can instruct them to isolate, and that will help you combat the disease. So, given some algorithms that use a fixed number of tests t, we'll decide which is best by saying which of them finds the most infected individuals. So specifically, we suggest this thing that we call ETI to decide which algorithms are good. And ETI is the expected number of tests per infected individual found. So that's a measure of the efficiency of these limited number of tests, even if we don't find every single infected individual. So just to belabor the point slightly, a test that takes on average t tests and finds on average k infected individuals has an ETI of t over k. That's the number of tests divided by number of infected individuals found. In this talk, we're going to look at two different models of pooled testing, which we call the theoretical model and the practical model. The idea is that the theoretical model will be like lots of the recent mathematical work done on group testing, as in the survey paper I mentioned earlier, whereas the practical model is more aimed at the current pandemic. And so the theoretical model might be of more interest to mathematicians, the practical model of more interest to practitioners. These two models have some things in common. For example, in both models we assume there's a large number of individuals, which we're modelling as n tends to infinity. So there's no danger that we'll run out of people to test. Also, in both cases, we use this independent infection model, where for this prevalence p, each individual is independently infected with that probability. However, there are some differences in the model. In the theoretical model that people have been studying recently over the past few years, they often take the prevalence to be tending to 0 as the number of individuals get big. However, in practice, it seems more likely that for the current pandemic, we'll likely have p constant, maybe 2% or 5% of people have the disease, but we don't expect that to change as we test more people. In the theoretical model, mathematicians like to assume that the tests are perfectly accurate. But in practice, we probably should allow for the fact that tests sometimes give the wrong result, as in a false positive or a false negative test result. And a lot of the theoretical work has looked at one stage, so-called non-adaptive algorithms. But in practice, it seems that we're probably willing to run an extra stage if it would help us find infected people quicker. For example, we might be willing to do one round of pooled testing, followed by some confirmatory individual testing in a second round. However, we're probably not going to want to do more than 2 stages because that will slow down how long it takes to get results from the laboratory back to the person being tested. So we're going to limit ourselves to 2 stages in the practical model, but only 1 stage in the theoretical model. So we're going to do the theoretical model first and the practical model second. So, quick reminder of the theoretical model, p tending to 0 tests perfectly accurate at 1 stage. So in this talk we're going to talk about 2 ideas here, one which we call cut your losses, and one which is a bit like a previous idea known as saffron. So let's look at the cut your losses. First, as a reminder, for the standard group testing problem, where we want to find every single infected individual, it's known how many tests are needed in the theoretical model. It's this number, it's whichever is bigger out of k log 2n out of n over k, and of 1 over log 2k natural log k. Where k here I'm using to be the average number of infected individuals, which is p times n. And it's known that this is best possible, so this is a solid result. So cut your losses is this idea. You'd like to have t star tests so that you could find everyone, but suppose you only had, say, half t star tests. In that case, cut your losses, say just look at half your people, because then you can find all the infected individuals in that set. That's not totally immediately obvious, but it is very easy to prove. Or if, for example, T star were 500, so you'd need 500 tests to test everyone, but in fact you only have 100 tests, then this says just look at 1/5 of the people, but find all the infected individuals in that 1/5. And that could have quite a good ETI, in that it could find 20% of your infected individuals, which is much better than if you'd been too ambitious, had tried to find all of them, but had missed lots. Obviously, if you have t-tests each day, then you could think of, just not everyone gets tested every day, but perhaps everyone gets tested once a week, for example. And so, given that solid known result there, the ETI is the same number, but just divided by k, so I've crossed out a k in each term, and that's what the ETI is of the cut your losses strategy. A second strategy is inspired by the saffron algorithm, which was an algorithm for a slightly different problem. The idea is to split the tests up into batches of 2 log 2 n over k. So presumably you've got some multiple of that number of tests available, and so you'll do that many batches. And to take 1 over p individuals, and so we can number those from 1 up to n over k, so individual number 1, number 2, number 3, and so on. And so we're going to use that batch of tests on those numbered people. And this is the cunning idea of the saffron authors. Let vi be the number I written in binary. Right, so because I is a number up to n over k, we'll need log base 2n over k bits to write the number I out in binary. And log base 2n over k is t over 2. Then write out w to be that number I written in binary, except swap the zeros for the ones. So it's kind of the flipping of the number v. And then stick those together. So v comma w is the number I in binary followed by its flip. So that's of length t, and it's weight t over 2, because wherever it's got 1s in the first half, it's got 0s in the second half, and vice versa. And we're going to place an item I in the tests, like corresponding to that vector. So that vector is the length, the number of tests, and for each entry where it's 1, we'll put that item in the test, and for each entry where it's 0, we won't. So let's think what happens. If our batch contains no infected individuals, all the tests are negative, and we can tell that, and that's all very easy, and we're done. If the batch contains exactly 1 individual, then out of these t-tests, the ones where its vector were 1s will be positive, and we said that that's exactly t over 2 of them. So we'll recognise this because exactly half our tests will be positive. So we'll know that there was only 1 infected individual. And not only that, because of this VW pattern we had, the positive tests will kind of write out the binary number followed by its flip. And so we can say, we can just read off which number it is that is the infected individual, and we'll find it. If the batch contains more than 1 infected individual, then more than t over 2 tests are positive, and will fail to locate which one it is under this strategy. This strategy can't manage to work out which infected individuals it is if there's more than 1. So it's this middle case that's the good one, right? The exactly 1 infected individual case, because that's when we find ourselves an infected individual, and so that's giving us a chance of a good ETI, because we're finding an infected individual. So since the batch size was 1 over p, it's just a quick Poisson calculation to show that the probability is e to the minus 1 of that happening. So our ETI is that 2 log base 2n over k is the number of tests we did, and 1 over e to the minus 1, that's the probability it works, and so that's our ETI. A regime that is often studied is where p scales with n like this, where small a means extremely sparse and a nearer to 1 means not quite so sparse. It turns out that for the most sparse cases, cut your losses is optimal. It's provably the best you can do. In the kind of middle regime, cut your losses is better than saffron, but in the dense regime, saffron is better than cut your losses. So there really are regimes where either of these is better than the other. But again, other than the very sparse case, it's not known if they're optimal, so maybe you can try and do better than the two ideas I showed here. Okay, and also the practical model we want to talk about. So as a reminder, this was where we sometimes have the wrong result. So a thing we know about PCR for COVID is that false positive results are extremely rare, but false negative results do happen, sometimes. And so our model will be that the very rare false positive results will actually be never. That will be a slightly convenient mathematical simplification for the purposes of what we do here. And we'll say that false negative results happen with probability U, as in a test that should be positive, with probability U actually does come out positive. So for individual testing, obviously testing n people requires n tests. On average, Pn of those are infected, and we'll only find them if their test really was positive as it should be, which is probability U. So this gives us an ETI of 1 over UP. Can we do better? So we'll look at this design where we have a first stage where each individual is in R pools, and each pool contains S individuals, and then if someone is in all positive pools in the first stage, they'll get an individual test in the second stage. That might be a bit complicated, but if R equals 1, if you think about this, we just get back Dorfman's algorithm that we talked at the very beginning of the talk. R equals 2 gives a kind of grid algorithm, which is that you place the items in an S by S grid, and then you do one test for each row and one test for each column. And then say we had 2 tests in the columns came back positive and 2 tests in the rows come back positive. Then we give individual tests to any items in the intersection of these. So if our S squared equals S times S items, some of them will get retested in the second stage. So that's what R equals 2 looks like. But it's sometimes of interest to take R equals 3 or bigger. So it turns out that this is the average number of tests per individual. This R over S is the first stage, and this term is the chance that the item goes through to an individual test. U to the R, because all its tests must be positive. P, because either it's infected, or Q here is 1 minus P. This is the probability that it's not infected, but it always shares a test with infected people. I'm not going to prove that in detail here, but it's not too difficult to show. The probability an individual is identified as infective. First, it must actually be infected, which is probability P. Then all R of its tests must correctly come out positive, and its one individual test must correctly come back positive. So that's U to the R plus 1. So that gives an ETI of this, the ratio of the two. Here's a table showing that for different values of the prevalence from 0.5% to 10%, and for different values of the sensitivity of the test from 60% up to 90%. The black digits are individual testing, and the coloured digits are this RS strategy. The orange ones are where Dorfman's R equals 1 are best. The green ones are where the grid algorithm R equals 2 is best. Blue algorithms R is 3. Note that Dorfman is used at high prevalence or low sensitivity, whereas R gets bigger for low prevalence and high sensitivity. And that's also where the gains over individual testing are the best, because the ETI is much lower, so it's fewer tests per infected individual found. So in the practical model, all of those parameters improved on individual testing, and what we just said about Dorfman and the grid algorithm. But again, can you do better is an interesting question. So that was my talk on pooled testing to isolate infected individuals, and you can find more details, including technical details, in the paper in the proceedings. Thank you very much for watching.